Okay, starting here, we're going to identify whether the function graph has an odd or an even degree and a positive or negative leading coefficient. So basically, we're doing the opposite of what we learned yesterday. Yesterday, we looked at a graph. Is that what we did? No, we looked at an equation, and we had to determine what the end behavior of the graph would look like. Now we're looking at the graph, and we're going to determine what the equation would look like. So if I'm looking at this one, I can tell that this is going to be an odd degree. Do you know why? It's going to be odd because my arrows go two different directions. One goes up and one goes down. If it was even, they would be both going the same direction. This case, it's also going to be a negative leading coefficient. So it's going to be a negative leading coefficient simply because this is starting by going up. So it's going towards positive infinity as x approaches negative infinity. And as x approaches infinity, it goes to negative infinity. So that's going to make that a negative leading coefficient. All right, next one. Tell me whether this one is odd or even degree and has a positive or negative leading coefficient. So for this one, it's going to be an even degree because they both point in the same direction, up and up. And then since it's an even degree and they're both going up, it makes it so that our leading coefficient is positive. So it's going to have a positive leading coefficient and an even degree. A turning point is where a graph changes from increasing to decreasing or from decreasing to increasing. A turning point always corresponds to a local maximum or a local minimum. For a function, f of x, f of a is a local maximum if there's an interval around a such that f of x is less than f of a for every x value in the interval except a. In other words, it's a local max if it's the highest point. If every other point around it on either side of it to the left and right, and it's directly around it, is lower than that, it makes it a local max. F of a is a local min if there's an interval around a such that f of x is greater than f of a for every x value in the interval except for that point a. Okay, so let's graph this on Desmos, simply because we don't have a graphing calculator. We will next week, though. Graph f of x equals 2x cubed minus 18x plus 1 on a calculator, and estimate the local max and min. So on the graphing calculators, there's actually a max and min function, or a way to do it. We're going to do graph. And I'll show you how to do it on here just because, like I said, you'll be back in school next week. And then we'll do it on Desmos. So doing it on the graphic calculator, you go into y equals 2x to the third power minus 18x plus 1. Push enter. And then we can do second trace, which access our calculate menu. And if I want to find the max, I go down to 4 and enter. So now for this one, I can see that I don't see the top or the bottom of the graph, so I'm going to have to zoom out first. So I'm going to zoom out. And now I can see the top of this graph here where it starts to come back down. So now I'm going to go back into my second calc and 4. Now I want to know on the left-hand side, so I go to the left of my peak here. Let me change this window a little bit. I'm going to do x min being -10, just so that you can see it well. -10 to 10. Let's look at that graph again. It's a little better. So now whenever I do second calc, I can do 4. I'm going to go to the left side of where it hits the peak. So it hits the peak somewhere in here. And I go left of that, and I click enter. And I go to the right of that and click enter again, and then enter a third time. And that finds my maximum value at x equals -1.732. Now again, this is not the only way to do this. We'll go back to the other way using Desmos in a moment. Find the minimum. We're probably going to use Desmos anyways because, well, I don't want to clean all the calculators. So 3 is our minimum. I go to the left. You can see where this bottom hump is. So I go to the left of that, and then I go to the right of it. Click enter again, and it gives me 1.73. So my max was at -1.73, and my min was at 1.73. By the way, this for the minimum should be choose 3 minimum, not maximum anymore. And that's how we do it. On Desmos, it's actually even easier than it is on here. I can enter my equation in. 2x to the third minus 18x plus 1. And now as I go to find a min and a max, you see it actually puts a point directly on it. So my max would be at -1.732, and my min would be at 1.732, which is exactly what we just found using the calculator. So 2 different ways to do it, both on Desmos and on the calculator. Should be very easy to find your max and min. All right, try this one. See if you can estimate the local max and min based on this equation. Whenever I enter this one in, you're going to notice that it goes up and up. My end behaviors, both of those going up. If I click on my lowest point, that's my min, because all the other points around it are higher than -6. If I trace this, these are all higher than -6 for our y values. So since those are all higher than -6, that makes this the min, plus, again, on Desmos, it points it out to you. So my minimum is at 0. It's the x value of that. What about a max here? Does it ever hit a top point where it starts to come back down again? No. So there is no max to this function. There's only a min. And sometimes you're not going to have a min, you'll have a max. Sometimes you won't have either. So it's just something to watch out for. In this case, our min is at 0. X equals 0, and you're done. All right, well, that was a tough section to get through. On Monday, we're going to handle some more information on this. maybe do some more example problems, some more actual work, and then we'll talk about our procedures for in class on Monday and how we move forward. All right, guys, have a great weekend, and I'll see some of you on Monday.